Okay. So in previous lecture, I think we have started this particular bit, but due to some network issue, I am not able to complete this part. Okay. So let's we discuss this particular bit once again. So the next part is the basics of SRM analysis. Okay. So while explaining principle of switch reluctance motor, I have told that the working of switch reluctance motor is generally based on variation in inductance. So the inductance associated with the stator winding changes, and that change is according to position of stator tooths and rotor tooths. So as rotor rotates, as there is a movement of rotor tooths along with a stationary stator tooth, the inductance associated with the corresponding stator phase get varies. Okay. So that variation is initially inductance rises, then that inductance remains constant. After that inductance falls, and again that inductance will remains constant. So how this variation is there? Why the variation is Why the variation in inductance takes place? That is inductance of stator phase windings takes place with respect to variation of the position of rotor teeth along with the stationary stator teeth. So we are going to discuss that particular bit in this. We are going to discuss that point in this particular bit. Okay. So for analysis of this particular concept, that is the variation in inductance, we have considered actually 8 by 6 configuration of a motor. 8 by 6 configuration means there are 8 stator slots or 8 stator teeth and 6 rotor teeth. Okay, that configuration is 8 by 6 configuration. So we have discussed that various configuration in construction of SRM. So this is actually your 8 by 6 configuration. So there are total 8 stator slots or stator teeth and 6 rotor slots. Okay. Now on these 8 stator slots, there are concentric coils. That coils diametrically or diametrically connected in series, so that there will be formation of 4 stator phases. And the inductance associated with each stator phase is generally varies with respect to the position of rotor teeth with respect to that stator phase. Okay, so when we consider, suppose if I say this is my phase A and phase A dash. So A dash is the one of the stator phase. So whenever this rotor moves, say we consider suppose movement of this rotor in clockwise direction. So whenever this rotor moves in clockwise direction, as this rotor teeth moves and as that rotor teeth passes in front of this stator teeth A, there will be variation in inductance. And for every rotor teeth, inductance will vary in that same way. That means, say we consider say stator phase A, when this one rotor teeth followed this particular stator phase A, then at that time there will be variation in inductance, rise in inductance, constant inductance, fall in inductance, once again constant inductance. For next teeth, whenever this A phase is excited, again that same variation will follow, rise in inductance, constant inductance, fall in inductance, constant inductance, and so on. So that variation we have to study, so that we are going to understand why that inductance varies and how that inductance varies. Okay, for this purpose this bit is important. So now, as I have already explained, SRM has no any winding or magnets on its rotor. So rotor is entirely a laminated structure of a magnetic material. It does not consist any sort of winding. It does not consist any sort of permanent magnet similar to stepper motor. If we recall stepper motor, then in case of stepper motor, variable reluctance stepper motor does not consist any winding or any permanent magnets. But when we consider permanent magnet stepper motor and hybrid stepper motor, that motor generally consists permanent magnets on its rotor. So in switch reluctance motor, as there is a no any winding present on rotor, the winding copper losses will take place only on stator side, because only stator consists of winding. That stator consists a concentric coil. So for say 8 pole motor, there are 4 phases, so 8 coils are there, and whenever the current flows through that particular coil, when we excite a particular phase coil, at that time there will be certain amount of copper loss takes place inside that stator winding. So there is only one source of copper loss in case of switch reluctance motor, and that copper loss is the copper losses takes place in stator. there will be no any copper losses in rotor. Therefore, this motor generally has a higher efficiency. As no copper losses are there, definitely the total losses will get reduced, and as total losses are less, the efficiency is more. Okay, so it only consists the source of excitation on stator winding, and this is an important feature which required that the resistive winding losses occurs only on stator. There will be no any rotor copper loss, and therefore we can make cooling easy. Why this cooling is easy? Because we can cool any stationary body easily. Stator is a stationary body, so we can cool that stationary body easily by according to size of machine. We can implement the different cooling techniques. So if machine is small, natural air cooling is sufficient. Okay, if machines are large, then we have to implement certain special cooling techniques, like oil cooling technique, or maybe some liquid cooling technique, or maybe force air cooling technique. So various cooling techniques are there. Okay, so under this particular case, if machine part is stationary, then we can easily employ a cooling method for that stationary machine part. So always it is easy to cool stator rather than cooling rotor winding. Okay, or rotor structure, because rotor is rotating part, and generally it is hard or it is difficult to employ a proper cooling technique for such rotating parts. Okay, so in SRM, as copper winding is only present on stator, there will be copper losses only takes place on stator winding, and copper losses is nothing but what is result of copper loss? There will be formation of heat. So whenever any winding carries current, there will be copper losses takes place, and that copper losses results in generation of heat. Okay, एक बार किसी भी winding में copper loss हुआ तो वहां पे heat formation होता है, and definitely that winding is placed on stator. So whenever the winding get heated, stator material also get heated. Okay, and we have to provide some cooling technique for larger motor. For smaller motor, such cooling is not provided, because there is no such heat formation in such small motors. Okay, so we can easily provide these cooling techniques for a switch reluctance motor, as there is only winding present on stator. Okay, and again it is more efficient and more effective. Cooling technique is also can be effectively provided, as winding losses are negligible, or as winding losses are less. Therefore, the efficiency of this SRM is more. Now, as I have already told, to produce torque in this SRM, there will be variation in the stator winding inductance. Okay, and that variation generally depends upon the position of a rotor teeth with respect to stator teeth. Okay, so that depends upon the position of rotor teeth. Okay, now how this variation takes place, we are going to discuss that variation in this particular bit. So that variation is when the rotor teeth, or when the inductance of stator winding varies with respect to rotor position in such a way that inductance is maximum when rotor teeth is aligned with a stator pole. So when there is an alignment, say this is my stator pole, and when rotor teeth is completely aligned with that stator pole, at that time inductance will be maximum. When rotor teeth move in forward direction or backward direction depending upon rotation, this total area where actual alignment is there, that area get decreases, and accordingly the inductance will get changed. Okay, accordingly inductance will get vary. If there is a no any alignment, ये rotor है, this is my stator. If there is a no any alignment, that means in this case the overlapping area is equal to 0 or minimum. Under that case inductance will be minimum. Okay, so in this way, depending upon the alignment of rotor teeth with respect to stator pole, there will be variation in inductance. Okay, and when that inductance is maximum, when the rotor or stator pole is aligned with a rotor teeth or rotor axis, and when the stator pole is not aligned with rotor axis, there will be minimum inductance. So the inductance is minimum when two axes are perpendicular. Perpendicular, that means there will be no any you can say that no any overlapping, or under this particular case if we talk about axis, so if say suppose this is my two pole motor, I think I have explained this bit in previous lecture, and say this is my rotor. I think you have studied synchronous motor. Okay, so this is suppose my rotor. So under this particular case, axis of rotor is this is the axis of rotor. So when the axis of rotor align with this stator axis, under that case we obtain maximum inductance. When axis of rotor is perpendicular, at that time there will be no any inductance. Okay, so that, or the inductance is minimum. Inductance will be minimum because inductance generally depends upon flux linkage. How we calculate inductance? Inductance L is always equal to the flux linkage divided by current. So current is the current flowing through stator coil, and under this particular case flux linkage will be maximum because जो particular flux है वो flux कौन develop करेगा? Flux will be developed by the stator coil, and that flux get linked with this maximum. There will be maximum flux linkage due to the rotor position, and under this particular case the inductance will be maximum because flux linkage is maximum. At 90 degree flux linkage to particular rotor pole will be minimum, and under this particular case inductance will be minimum. Okay, so according to the alignment of this rotor teeth with respect to stator pole, there will be variation in inductance. So whenever stator teeth and rotor poles are in alignment with each other, inductance will be maximum. When they are perpendicular to each other, inductance will be minimum, and in between these two condition, one is maximum, another one is minimum, the inductance get false. Okay, and we are going to study that particular case. So now for analysis of this SRM, we consider certain terminologies. So that terminologies we have already discussed in previous class, but let's recall this. So let alpha S is the stator slot angle in degree and alpha R is the rotor slot angle in degree. Now what is stator slot angle and rotor slot angle? So whatever this particular distance is there, this is actually your stator slot angle. Okay, because slots and teeth, I think you are familiar with this. Okay, slots, or so there is slot, and in between two slots, in between two slots there will be one teeth, or if we consider there are teeth, in between two teeth there will be slot. Okay, so whatever angle or this distance is there, that distance is actually rotor slot angle, stator slot angle, and alpha R is the rotor slot angle. One second. Okay, so alpha S is the stator slot angle, alpha R is the rotor slot angle. Next, beta S and beta R. What is beta S? It is the stator pole arc in degree, and beta R is the rotor tooth arc in degree. So this is actually pole arc, or you can say that teeth arc, stator teeth arc, and this is rotor teeth arc in degree. Next, we consider NS and NR. NS, you are familiar with this term. NS is the number of stator poles. NR will be the number of rotor teeth. Now in this particular case, number of stator poles equal to 8. Number of rotor teeth is equal to 6 because we consider the motor configuration as 8/6 configuration. 8/6 configuration. Okay. Let TC will be the turns per coil. That is turns of stator coils. So as I have already told now, 8/6 configuration. So how many concentric coils are there? There will be 8 concentric coils diametrically connected in series, so that there will be formation of 4 stator poles. Okay, so here total 8 coils are there, and each coil carries number of turns equal to TC. R will be the radius of rotor at air gap. That means if I consider this is rotor, then from this is actually center of rotor. So from this, the air gap radius will be the R. Okay, so this is actually air gap. So this much radius, whatever this radius is there, this radius is actually radius R. Okay, that is denoted by capital R. Next is G is the length of air gap. Okay, so whatever length of air gap, this is the length of air gap. Air gap between stator and rotor. So this length of air gap is G. Then L will be the inductance per phase. L, capital L, is the inductance of winding, stator winding per phase. So per phase inductance is L. Now again, if we consider inductance of any one phase, same inductance will be there for remaining phases because windings are identical. windings are identical. That identical winding means that windings are wounded with a wire with which has same gauge. Gauge is nothing but your diameter of wire or radius of wire. Okay, so that are wounded with a same gauge wire. Again, that consists, each winding consists equal number of turns. Therefore, inductance is same. Okay, each winding carries same current. Why same current? Because if you recall excitation circuit, that excitation circuit of winding is excited with a same DC supply. Every winding is identical. As winding is identical, its impedance is identical. Impedance of each stator winding is same. So if impedance is same, that will carry same current. Okay, winding is identical, impedance is same, that will carry same current. Indirectly, inductance is also constant because L is equal to what? It is flux linkage divided by current. So L is same. So L is the inductance of each phase, and that all phases have same inductance. Let Q is the overlap angle. Now this Q is overlap angle between rotor teeth and stator slots, or stator poles and rotor teeth. So whatever angle of overlap is there, that angle is angle Q. Mu zero is the permeability of air. Mu zero is the permeability of air, and theta will be the rotor displacement in degree. Okay, that means by how much degree theta will displace. Now let's assume there will be no fringing of a flux. Now what is meaning of fringing? So fringing is actually the leakage concept of flux, leakage flux. So there will be no any fringing, means whatever flux which is generated by the particular stator phase, we consider entire phase get linked with the rotor. There will be no any leakage flux, or there will be no any deviation in that flux. So जो भी कुछ flux stator winding का phase, particular phase generate करेगा, वो सब flux क्या होगा? That all flux get linked with the rotor teeth. Okay, so there will be no any fringing, and the flux to be confined entirely in the overlap of a rotor, whatever thing which I have explained now. So entire flux get overlapped with the rotor teeth. Okay, there will be no any loss of flux. So under this case, inductance is equal to, okay, so there is a direct formula for inductance. If you required, I will provide derivation of this inductance also. So I have that derivation with me. I will circulate that derivation on your Google Classroom. Okay, so at this moment it is not necessary to explain that derivation. Okay, so L is equal to Tc square into mu 0 L Rg, L into R into Q, sorry, L into R into Q divided by 2G, where I into R into Q represents the area of air gap. Area of air gap. Okay, so why this area of air gap is this? Air gap, it is completely cylindrical air gap. Machine, this is actually whatever look is there, that look is actually 2D. Actual machine is complete 3D diagram. So air gap is completely cylindrical. So dimensions, what are the dimensions? Dimensions are air gap is radius for that entire air gap from center of machine, length of air gap. Okay, so that is length of air gap. That length is actually G, which is the length of air gap. Again, this L is complete length of your rotor. कंप्लीट लेंथ ऑफ रोटर, सिलेंडर है तो उसका एक रोटर का लेंथ रहेगा कंप्लीटली, सो दैट लेंथ इज लेंथ एल. ओके, एंड आर इज द रेडियस ऑफ रोटर और रेडियस ऑफ रोटर एट द एयर गैप. देयरफॉर दिस I into Q into R, this will be the area of entire air gap. Okay, so L is equal to Tc square into mu 0 LRQ divided by 2G. Now the variation of this inductance can be studied with the help of this diagram. Okay, so here if you look this diagram carefully, we consider machine as a 8x6 configuration machine. For sake of simplicity, here we have represented only 3 stator poles and 2 rotor teeth. So this is the circular view of the machine. For again simplicity, if we draw longitudinal view of that motor, longitudinal view means straight view. So that straight view looks like this. So this is the stator. Okay, so this structure is actually stator structure. So that stator structure, so there are two different stator poles are shown over here. This is rotor. If we consider rotor rotates in clockwise direction, if the direction of rotation of rotor is in clockwise direction, here that movement is from left side of screen towards right side. Okay, that means rotor rotates in clockwise direction. So this is the direction of rotation of rotor. Means if we draw its longitudinal view, this will be the direction of rotor. This will be the direction of rotor. Okay. So stator, these particular poles are stationary. Stator poles are stationary and rotor will move in this direction. This is actually longitudinal view. Now consider only phase A or stator pole A and rotor teeth B. So I have here there are total 4 positions of rotor teeth with respect to stator pole have been drawn. If you look towards that 4 position at this particular stage, there will be start of overlapping. Okay, जैसे जैसे ये रोटर मूव हो जाएगा, जैसे जैसे रोटर रोटेट हो जाएगा, now there will be starting of overlapping. Okay, now after some time this B phase get overlap with the A, B teeth or B pole of rotor get overlap with the stator phase or stator pole. Okay, so at this point there will be starting of overlap. If you look towards this second, what will happen? There will be maximum overlapping takes place. That means entire stator pole get overlap with the rotor teeth. Complete stator pole is get overlap with the rotor teeth. That is the second position. What is third position? Now again, as this rotor moves in clockwise direction, now after this, as rotor moves forward, the overlapping start decreasing. Okay, overlapping start decreasing and at last there will be overlap ends. So at each and every phase which is under excitation, same relation or same variation in overlapping is there. So whenever that rotor teeth or rotor, suppose this is my stator pole, whenever suppose this is my rotor teeth, so at this point there will be starting of overlapping. When this moves in forward direction at one particular point, the complete stator pole and rotor teeth are in overlap with each other. This will be the maximum overlapping. After this, again as rotor teeth moves, the overlapping angle get decreases, overlapping decreases. At last, what happens? Overlapping completely ends. But at the same time, there will be overlapping with correspond to another phase. But for sake of simplicity, we consider only phase A. Okay. So these are the 4 positions where the rotor teeth get overlap with the stator pole. Now, how variation takes place? We know that whenever stator pole and rotor teeth are aligned to each other, at that time there will be maximum overlapping, there will be maximum inductance. As overlapping angle goes on decreasing, there will be fall in inductance. Whenever there is a no any overlapping, inductance will be minimum. Okay, so that is actual rule for variation in inductance. So same logic we can apply. So here the position of stator pole A and rotor tooth B when the overlapping begins are shown. So I have explained that thing. So at this particular case, overlapping starts here. There is the starting of overlapping. So initially phase A inductance is minimum because overlapping is not there. At this point, what will happen? There will be starting of overlapping. Therefore, there will be variation in inductance. That variation is rise in inductance. The inductance will rises. Okay. So from this, as this rotor teeth B moves in forward direction, the overlapping increases and there will be rise in inductance. Okay. So here same statement you will find. The inductance start increasing at this particular instant. Now, this position is taken as a reference and we consider the rotor displacement is 0. Okay, so we consider that as a reference position. At B figure, there will be inductance maximum because here the maximum possible overlapping is there. जैसे जैसे rotor move होगा at one particular instant, the inductance will be maximum. Inductance will be maximum, and then after there will be fall in inductance. So at here, the entire stator pole is a overlap with a rotor teeth. Therefore, inductance will be maximum. So if I draw the variation of inductance, okay, sorry. Okay, so at this point, say in 1, there will be rise in inductance. Okay, here this is what it is, the position B. It is position B. This is now your position A. It is position A where there is a starting of overlapping. From starting to maximum overlap point, inductance will rises. Now at this moment, what happens? Again, rotor moves in forward direction here. But there is a this much portion of rotor which is more than stator teeth. So whenever the rotor crosses up to this much length, the inductance remains constant because under that case, entire stator pole is in overlap condition with the rotor teeth. So inductance will remains constant. Inductance will remains constant. So from this to this, inductance will remains constant. After that, यहाँ पे क्या होगा, तो ओवरलैप एंगल जो है वो ओवरलैप एंगल कांस्टेंट रहेगा जब तक ये रोटर इतना डिस्टेंस कंप्लीट नहीं करता. आफ्टर दैट द ओवरलैप एंगल गोज ऑन डिक्रीजिंग. आफ्टर दैट ओवरलैप एंगल गोज ऑन डिक्रीजिंग. सो हियर देयर विल बी decrease in overlap angle, so the inductance again start to fall. At one particular point, the inductance will be minimum when the overlap angle is minimum, and then after again inductance associated with that particular phase remains constant. Inductance will remains constant. Okay, same explanation you will find over here. So at B, the condition when inductance reaches its maximum value, then at this particular position, so this figure indicates the instant at which overlaps start decreasing, which is the figure C. So when there will be overlaps start decreasing, inductance begins fall. There will be falling of inductance. The instant at which overlap ends, at that time overlap is 0. Inductance will be minimum. That inductance will attain its minimum value. Inductance will attain its minimum value. Okay, and this variation is shown in this particular figure. That figure is, you can see over here. So initially inductance is minimum. Okay, then inductance will rises, that will attain maximum value. So at this point there will be maximum overlapping angle. After that inductance remains constant. Then the overlapping angle goes on decreasing. Inductance start falling. There will be fall in inductance. When overlap ends, again inductance will remains constant. So in this way, there will be variation in inductance, and due to this variation in inductance only, the torque will produced in switch reluctance motor. Okay, so L theta profile, whatever L theta profile, theta is what? It is the rotor displacement. Rotor displacement. So if we draw L theta profile of the SRM, that indicates for 0 to beta s, that means up to this position, this is the beta s. For 0 to beta s, the inductance rises from L minimum to L maximum. In between beta s to beta r, beta s is what? Beta s. Okay, this is beta s. So beta s to beta r. So here what is beta s? This is actually your beta s. This is beta r. So in between beta s to beta r, the inductance remains constant. Inductance remains constant. Then from beta r to theta is in between 2 pi divided by ns. That ns is what? It is the number of stator poles. Okay, so 2 pi divided by ns. So for this particular case, the inductance start decreasing and reaches to L minimum when theta is equal to 2 pi by ns. 2 pi by ns, and in between 2 pi by ns to again 2 pi by nr, the inductance will remains constant. After that, again same cycle will begins. That means for phase A, again there will be rise in inductance, constant inductance, fall in inductance, constant inductance. So in this way, the inductance of switch reluctance motor varies with respect to rotor position, and due to this variation in inductance, there will be induction or generation of torque in switch reluctance motor. Have you understood this? Yes, online members.
Yes, sir.
Okay.
Yes, sir.
Okay. Yes. Yes. So that is about the analysis of inductance. If you require derivation for this, I will upload the entire derivation of this inductance L for switch reluctance motor on your Google Classroom. Okay. So go through that particular derivation. Okay. So now for this lecture, we will stop here because next bit is somehow larger bit, that is torque equation and characteristics of switch reluctance motor. Okay, so we will discuss this particular bit on next lecture, that is on tomorrow.